Modern AI engineering suffers from a strict operational bottleneck. Deploying an agentic system is highly accessible, but improving that system post-deployment is incredibly difficult. Aligning large language models through preference-based training methods like RLHF or direct preference optimization requires meticulously curated pairs of behavioral data. You need concrete examples of the model succeeding and failing to adjust its policy. Sourcing those examples from production is a volume problem. Deployed agents generate massive, complex execution paths. These logs contain natural language, tool calls, runtime events, and environmental feedback, creating non-deterministic paths that cannot be easily parsed at scale. To sort through this, the standard industry workaround relies on an auxiliary model. Using an LLM as a judge, developers run every single generated trajectory back through another massive neural network to evaluate its quality. This chart plots agent trajectory volume against evaluation API costs and latency. We see that evaluating every trajectory with a secondary LLM scales exponentially. As traffic grows, the operation quickly crosses into financial and architectural failure. Falling back on manual human review is equally impractical, given the sheer volume of logs generated by high-traffic enterprise applications. Without a new architecture, the AI industry lacks a sustainable mechanism to convert production telemetry into the training signal required for continuous optimization. To solve this, engineering teams must stop evaluating trajectories for nebulous concepts like quality or correctness. The focus must shift to a specific metric: informativeness. An informative trajectory is one that contains enough concrete behavioral evidence for a developer to formulate a hypothesis on how to improve the model. Traditional conversational quality metrics attempt to assign scores or prescribe subjective fixes based on context. A terse response might be perfect for an expert, but frustrating for a novice, making automated scoring highly unreliable across different domains. Informativeness, conversely, can be extracted from raw logs using a deterministic, signal-based framework. It relies on observable behavioral markers and requires zero neural network computation to execute. Applying these zero compute parsing rules bypasses expensive model calls entirely. It filters out the noise and surfaces the exact high-value data pairs needed for training. To apply deterministic rules, we first have to model a single agent interaction as a multi-track timeline. The top track is the discourse layer. This contains the natural language exchange, the user's prompts, and the agent's conversational replies. The bottom track is the execution layer. This represents the internal control loop, consisting of the actual tool invocations, database mutations, and API responses happening behind the scenes. Relying solely on conversational metrics creates a massive blind spot. Here, an internal tool call fails entirely, yet the agent maintains a positive, helpful conversational tone in the interface. An agent can generate perfectly fluent text while catastrophically failing its backend tasks. Robust triage demands parsing both of these layers independently. We categorize the telemetry into specific domain-agnostic signals, depending on which track they originate from. Treating complex autonomous agents like simple chatbots completely obscures the severe execution failures masked by clean text generation. We begin with the top track. Interaction signals operate exclusively on the discourse layer. They use lightweight lexical matching and string similarity to detect patterns in the conversation. The first signal is misalignment. This triggers when a user must heavily rephrase a prompt or restate constraints to make the agent understand. Misalignment does not assert that the agent is factually wrong. It simply flags that a shared semantic understanding has failed to materialize between the user and the system. Next is stagnation. This identifies near-duplicate discourse responses. The agent continues replying, but the conversation makes zero logical progress. Finally, we have terminal markers, disengagement, and satisfaction. These trigger on explicit session exits, like a user typing "talk to a human," or confirming success with a phrase like "that worked." Tracking these linguistic heuristics allows the system to accurately flag human-legible failure and success modes. Crucially, it accomplishes this without requiring any semantic comprehension from an LLM. Shifting focus to the internal control loop, we implement execution signals. Because these deal with deterministic runtime events, they require structured log parsing rather than string matching. The first logic flag is the failure signal. This is defined strictly as an attempt that yields an empty result, or a no-op action linked to a specific tool invocation. The most critical agentic failure mode is the loop signal. This captures repetitive control flow where the agent remains active but makes no forward progress. Execution loops take multiple forms: identical tool retries, oscillation between different search strategies, or progressive parameter drift that fails to resolve the user's intent. The final category is environment signals. These represent external system constraints rather than flaws in the agent's internal logic. Environment signals track external realities, API rate limits, malformed server responses, or context window overflows. There's a strict architectural rule for environment signals. They must be isolated for system diagnosis. They should never be used as preference learning data. Penalizing an agent for external infrastructure limits during preference training introduces spurious correlations. It trains the model to anticipate external failures, actively degrading its core reasoning capabilities. To empirically validate this zero-compute triage method, researchers tested it against the TauBench dataset, a rigorous environment for evaluating tool-augmented agents. The study compared 3 distinct sampling strategies for extracting useful logs: 1. Random sampling, 2. Heuristic sampling, and 3. Signal-based triage. Heuristic sampling represents the common industry baseline, where engineers simply filter logs by conversation length or total turn count, assuming longer interactions contain more errors. This vertical bar chart shows the baseline informativeness rate. Random sampling yields 54% actionable data. Heuristic sampling improves to 74%. The signal-based strategy surges past both, achieving an 82% informativeness rate. Roughly 4 out of 5 flagged trajectories contain concrete, actionable evidence for developers. In economic terms, signal sampling yields a 1.52x efficiency gain per informative trajectory compared to the baseline. Deterministic zero-compute rules actively outperform standard heuristics in servicing highly actionable training data. The heuristic baseline suffers from a hidden flaw. Filtering by mere interaction length predominantly oversamples obvious catastrophic failures. Finding catastrophic failures in a log is computationally trivial. The actual challenge in MLOps is identifying what we call informative successes. This grouped bar chart focuses exclusively on trajectories categorized as successful. Random sampling captures 41.3% informative data, and heuristic reaches 50%. Signal triage significantly outperforms them, yielding a 66.7% informativeness rate among successes. An informative success is a trajectory where the final task was completed, but the internal log reveals subtle policy violations, inefficient tool use, or minor execution loops along the way. These subtle inefficiencies provide the exact contrast data required to refine a good model into a great one using direct preference optimization. By decoupling basic observability from heavy LLM evaluation, engineering teams secure massive compute cost savings without sacrificing diagnostic rigor. Implementing a structured signal taxonomy creates an always-on zero-compute pipeline. It continuously feeds high-value alignment data back into the engineering loop, scaling endlessly without bankrupting the system.